Welcome. We're thrilled to have you here, and we're thrilled to welcome back Dennis Whyte, who's our distinguished visitor today. Everybody seems to have grabbed a seat and found their spot and cleaned their hands and put on their masks, which is terrific. This is just a real treat to have on a Monday morning. What a great way to start the week. And I also want to acknowledge that we are in the library learning commons, that you see there are no books left in this space. And as the books got taken out, the students filled it more and more and more. So during the term, this place is abuzz, and we would never be able to use it for an event. So in some ways, we're lucky that all the students have left campus. So we want to have this engagement. We want to have the libraries be hubs for people to come together and exchange ideas. And that's exactly what we're going to do today. As we gather together here on Treaty 6 territory, I do want to acknowledge that the land we share is got a long heritage with Indigenous people. It's a land that we all share the stewardship responsibility for, and that we have the opportunity to come together in community, respecting all of the people who've been involved in building our community, and all of the different heritages we share and the ideas that we can bring together. This is also a territory occupied as the traditional territory of the Métis, and those people have their own history and their own sense of place and their own context in the planet we call home. We were able to bring in Dennis Whyte for this talk and associated with his Distinguished Alumni Award as a Cheriton Distinguished Visitor. Ross and Muriel Cheriton established this award in 2011 through a generous gift to the USask College of Engineering. The fund's goal is to highlight individuals with an engineering degree who have found success in life and in their career that is founded in some way through their degree from the University of Saskatchewan, and bring them to the forefront of our engineering community. We do that today through a public lecture that has brought together students, faculty, and alumni from across campus and from the engineering community at large. Today's gathering is quite timely, as William Cheriton passed away earlier this year. And much like our guest lecturer, Ross grew up on a farm in southern Saskatchewan, attended USask for his undergrad, and studied engineering physics. I want to mention that his wife, Muriel, was the first female Iron Ring warden in Edmonton. And when I was named to be on the camp, she was like the den mother to all of us. And so we always looked up to Muriel and really enjoyed her contributions at the table. So I have a bit of a personal connection to this fund, and I'm really delighted to be welcoming Dennis under its umbrella. So Dr. Dennis Whyte is an alumnus of the USask College of Engineering, having studied engineering physics and completed his bachelor's degree in 1986. He went on to earn his master's and PhD at the Université de Québec. He is the Hitachi America Professor of Engineering at MIT, a professor in the MIT Department of Nuclear Science and Engineering, and the director of the MIT Plasma Science and Fusion Center. He has led teams, his interests focus on accelerating the development of magnetic fusion energy systems. And the soundbite explanation of this I found was, think what happens on the sun. We want to make that happen in a controlled way. He has led teams and published over 350 papers across the multidisciplinary fields of magnetic fusion, including plasma confinement, plasma surface interactions, blanket technology, plasma diagnostics, superconducting magnets, and ion beam surface analysis. He leads the overall MIT research team on SPARC, which is a private sector funded compact high field tokamak, presently under development to demonstrate net fusion plasma energy gain. He also leads the Laboratory for Innovations in Fusion Technology at PSFC, which has energy company sponsorship to explore early stage disruptive fusion technologies, which all sounds like a tremendous amount of fun. And I can't resist giving a nod to our colleague from the University of Waterloo, who was having so much fun with her physics that she thought applying to be a professor was a waste of time. And it caused them great embarrassment when she got a Nobel Prize and they had to do the application for her. So I think that those who do physics for a living have a tremendous amount of fun. I'm really looking forward to this talk, and I'm really thrilled that all of you could come and join us this morning. So Dr. Whyte, please take the stage.
Oh, thank you so much. Actually, I know her. She's amazing. Yeah. Right. So, it's great to be back. The memories are flooding back of some well-spent and some other interesting times here at the college. Yeah, it's great. So I'll just get right to it. So what is the lecture about? So this is about fusion. So fusion is simply the power source of the universe. So as you know, we have a lot of challenges around energy and how we make clean energy in a sustainable form, actually to protect ourselves and the climate. And the way I say the universe is already voted. Fusion is actually the power source of the universe because almost every energy source we use is actually fusion at its core. Solar power is fusion because it comes from the sun. Wind as well too. Actually, oil and petroleum is also fusion power because it's just basically stored solar power far beneath the Earth. And stars work by the fact that they're very large balls of hydrogen, the most abundant element in the universe. And they basically convert that hydrogen into helium to make energy. And we know how effective an energy source it is. It lasts for tens of billions of years in our own sun. On Earth, the idea is that we bring it, as the dean said, we bring it down to Earth as a sustainable terrestrial energy source. And what we do is we take the heavy forms of hydrogen, you see these on the right, the deuterium and tritium, we fuse them together, they release net energy as a result, and we can do something. So we're gonna walk down the path here a little bit. So first of all, so fusion is a really, excuse the pun, hot topic in the last 10 months. With announcements not only from our own laboratory, but also laboratories around the world, which are pursuing this because it feels like the race is on. It's actually not the race against each other, it's actually the race against climate change. And we are engaged in that. And I'll sort of comment to this is my colleagues in the United Kingdom, my colleagues in California, and ourselves at MIT as well too. And I'll hit these as we go along. So it often confuses people because you hear about this, and it has nuclear fusion in front of it. And it's like, well, how is this like nuclear energy, which is a very important part of our energy makeup right now. So fusion arises from a fundamental science that comes from how nuclei are put together, which makes up 99.99% of the mass of the universe. And it's this curve, which is the first thing we teach nuclear science and engineering students. And what it turns out is that the most stable of the nuclei is iron, 56. And then on all the other sides, all the other elements are less stable than that. So what this means is that when you rearrange them into different elements, actually, you release energy. So fission is the thing that occurs on the far right, that you split apart the most unstable nuclei, and when they go apart, you make net energy. Fusion is the exact opposite. You go over to the lightest elements, you fuse them together, and when you fuse them together, by the way that nuclear physics works is that helium, which is a very light and abundant element, has an extremely stable nucleus. So when you rearrange it into helium, this is what happens. This is what our star does. A sun basically is a conversion engine between hydrogen and helium. And it's opposite. So there's going to be numbers in this. So when you ask an MIT professor to come give a talk, there's going to be log plots and there's going to be numbers, okay, with units on it. So why is this important? So fusion, so start with, we have this funny unit of energy, MeV, because this is what we use in nuclear energy. So it's many tens to hundreds of MeV per reaction. Why is this important? It's because the most violent chemical reaction, which is like burning petroleum and so forth, is 1 electron volt. So every reaction that comes from these that releases net energy releases an order of 10 million times more energy than you can ever get for a chemical reaction per unit mass. That's why it's environmentally so benign, because there's almost no fuel involved. But the threshold temperature versus fission and fusion is very different. Fission actually happens at room temperature. In fact, there are naturally occurring fission reactors they find them in tar fields and so forth in Africa. Fusion happens at temperatures like the center of the sun, a threshold temperature of around 50 million degrees. Wow. But, and here's the big one, is the one that comes below, is that the products of fission have to be hundreds of radioactive isotopes that are produced by the splitting apart of this very unstable uranium nucleus. You get gammas and so forth. Fusion releases two things, helium and a neutron, which I'll get to. And helium is a benign, safe, inert gas. So we'll walk through this. So what is fusion energy? It sounds very exotic, but it's actually recycling. That's the theme I'm going to use. Fusion works by recycling its own energy and its own particles. So how does this work? So I'm going to use these funny units. I'm going to walk around because I'm a professor, so you always walk around when you talk. So what is it? So before you take deuterium and tritium, these are these heavy forms of hydrogen. That's all they are. And you get to the condition that they're at this unit in MeV of 0.01, which sounds very small. But 0.01 in these units, if I convert it into a temperature, is 100 million degrees Celsius. Oh, we'll get back to that. Vroom, you fuse them together, and on the other side, it's actually the same particles, but you've rearranged them. And out comes a helium and a neutron, and these are their energies. Where is fusion energy? Fusion energy is in the products that are made by the fusion. And they come out with much larger numbers than at the beginning. This is the 1,000-fold energy gain that you get from fusion. Spectacular. Okay. So then what do we do? Well, the products are helium, which is the heavy one down at the bottom, and it has 1/5 of the fusion energy because it's more massive. So what we do is we take that one, and it has electric charge on it, and because it's a part of the fuel, it's forced by basic physics collisions called Coulomb collisions to give its heat back to the fuel. So it's simply recycling its energy back into this. And because helium is one of the most stable nuclei in the universe, it cannot undergo any further fusion, which is brilliant, because this means the thing that you make cannot make any more fusion reactions. It can only keep the fuel hot. So therefore, a critical runaway reaction that can happen in fission is physically impossible in fusion. This is why it's one of the reasons it's so safe. And so I plop up the news story that came, this was last summer, is that our colleagues at the Livermore Laboratory in California showed that with lasers, they're actually able to get to the condition for the first time when they saw those hot helium particles being the dominant source of the heating in the plasma. All other conditions to date is we took external sources and made the plasma hot. It started to keep itself hot. Very, very exciting, a threshold to get by. But what about this other particle, neutron? So neutron is one of the subatomic particles that makes up the nucleus, and it has no electric charge. And because it has no electric charge, it's not part of the plasma fuel. So our own sun, for example, is made out of all these charged particles. And it lacks a charge, it immediately escapes the plasma, and this means it escapes the fuel, and it has 80% of the fusion energy. So what we do is we stick stuff in front of it, and by the rules of nuclear physics, like how energetic, how fast is this particle? So if I was to let it go, and I remember my wife and I, it took us 22 hours to get here that's a whole different story about airlines. From Boston on the airline, it would go from here to Boston in around 1/3 of a second. That's how fast it's going. The energy is extraordinarily high in this. But it turns out we have to put stuff in front of it. What I mean by stuff is like it has to be in the solid and liquid phase. So that by the interactions, what happens, it basically does billiard ball collisions. It hits those particles and it creates heat. And fusion, and this is really important because fusion sounds exotic, it's literally just a heat source. Like it gets things hot, a liquid or a solid. And that's what makes electricity. And in fact, we get that helium to give up all its energy. It actually comes back down to room temperature in a space of about like this big. So then we do something very clever. We make this material, there has to be lithium around in this because we exploit another reaction. That at room temperature, that lithium and that free neutron undergo another kind of reaction. And it actually releases more energy, and it releases another helium particle, and it releases a tritium. And I didn't talk about this. What is this tritium? Well, so deuterium is naturally occurring. Tritium has a very short lifetime, and so it decays in nature. There is no tritium source. This doesn't sound like a good energy source. There's no fuel source. So the thermal neutron interacts with that lithium, makes tritium, and then you take that tritium particle and you recycle it, and you put it back into the plasma. So it's a fuel system that actually creates its own fuel. I know that sounds like cheating, but that's actually because it's the wrong way to describe it. Tritium is not the fuel of fusion, it's the catalyst of fusion. So it's the equivalent of what you would have in a chemical reaction. So in the end, it's very interesting. What are the consumables in fusion? It's deuterium and lithium. And there's deuterium. It's a good time to take a sip of water. There's enough deuterium in this bottle to power me, like all of my energy uses, for several years. Yeah, wow. I'll take a sip just so that sinks in. And lithium is so abundant. This isn't lithium in car batteries. Remember, 20 times millions. So you go through this, it's essentially an inexhaustible fuel source. And the ash is helium, which you blow up kids' balloons for your party. Well, maybe that sounds way too simple, Dennis. Oh, that is way too simple. But you got to remember, those fundamentals are there. It's why we pursue fusion. At its heart, it has physics advantages that are just almost insurmountable to overcome. It turns out it's practically hard to make this work, but we're getting closer. So now we get to this, and actually about the College of Engineering and so forth. So what do we actually do? Well, so it turns out you have to make like outer space. This occurs in a hard vacuum. You eliminate all the other particles away from there. So under a hard vacuum, you've got to put materials around this because you're going to make this exotic fuel because it's got to capture the energy. Oh, but this neutron, remember I told you it would go from here to Boston in a third of a second? Well, it's going to knock the heck out of those materials. So those neutrons actually alter the surrounding materials in a fundamental way. It actually can do that. And then inside of this, it also alters the interior surfaces because it's like putting things on the surface of the sun. So in the end, all this I went through, you could already see I touched on plasma science, I touched on nuclear science, I touched on material science, I'm probably forgetting a few ones in there as well too. And in the end, this is what, and my education here was so important to this. It is the most multidisciplinary field you can imagine. I have had the pleasure to work in almost all of those areas, as you listed in the comments. Okay, all very nice. Now let's get to practicalities. The problem is, so why is this hard? Because what happens in a sun is that in order to get it hot, you need a containment system. And the containment system of the sun is its own gravity. It's just its own mass. So at the center of the sun, it can basically hold itself. But gravitational force, it turns out, is a very weak force. It's the weakest of the natural forces. And we replace this with another force that we can use on Earth, and it's actually much stronger because it needs to be contained in this. So what does this mean? Well, we actually replace that force with a magnetic force. And the magnetic force is such that, so maybe I'll just make a quick word about plasmas. That's this plasma science. It's not blood. Plasma is the fourth state of matter. And what happens, you go from a solid to a liquid, and you get a hotter liquid turns into a gas. And when you get above 5,000 degrees, then everything turns into a new state of matter. It's called plasmas. And it never gets taught in school. Maybe one of my legacies we actually teach this is the fourth state of matter in elementary schools, because it makes up only 99% of the universe. Because what's that? Because it's stars. All stars are above 5,000 degrees. So everything's in the plasma state. So everything's hot, right? It's around above that. And what this means, the characteristic of a plasma, is that it's gotten so hot that actually the individual atoms, like the atoms in this room, get pulled apart. And they have separate charges now of negative and positive, equally balanced to each other. So we exploit this force called the Lorentz Force, which is a magnetic field, which forces the plasma particles to basically execute loops around the lines which are there. And the key thing to remember here is that this force goes like the charge times the velocity, those are basically fixed, times the strength of the magnetic field. So what it says is that a larger magnetic field means a larger force and a better containing force, and that both electrons and ions are confined because both negative and positive charged particles are confined. So how do we do this on Earth? We build a system that looks like this. Because you say, well, how can you hold something at 100 million degrees? You can't. In fact, if you try to hold it, what happens is the plasma just gets cold. And it sounds dangerous, 100 million degrees. It's the opposite of dangerous because it actually it doesn't want to stay hot. So you basically trick it into not knowing it's on Earth. It thinks it's a star. So you build a containment system that is built out of electromagnets. And how do you do? So that magnetic force comes from an electromagnet. An electromagnet is simply, you take electricity and you put it in a loop, and it's going to make that magnetic field. And we put them into a configuration like this. And we have and you said it right, called a tokamak, which is a Russian acronym for basically a donut-shaped, in Canada, we should talk about donuts. Canada, Tim Horton-shaped donut, that was a good one, that is in a donut shape that was made with these electromagnets. And the physics of this is very well understood. And you basically push this around. So why is this important? It's because the thing that's making the force is doing it without physically touching it. It's an action at a distance. So these electromagnets actually have no idea they're confining the plasma, and the plasma has no idea it's being confined by the magnetic field made by these electromagnets. It just feels it like this. So that's how you trick it. And what are the conditions necessary? We've actually known about this since the 1950s. It's like making a bonfire. Remember, because it's about keeping hot. You got to have wood density. You have to have enough wood. You basically get it hot with a match, and then you put the logs together so that one log, when it's burning, keeps the next log burning as well too. We've all made a fire, most of it. Except just the conditions change like just a little bit. So the one that really blows people away is the temperature has to be 100 million degrees Celsius. Just a little different than Earth. But here's the interesting thing, is that the density of the fuel is 100,000 times less than the air that you're breathing right now. So there's very, very few particles, but they're very, very hot. And in the end, this means that the pressure or energy density is very low. And then basically you configure the logs, like the magnetic field, such that if you can find a unit of energy for an order of a second, then what happens is it becomes a star. And at that point, fusion actually, the whole thing starts heating itself. Again, I warned you, a couple equations, just because I'm in engineering school, I got to show a couple of equations, show my education here wasn't wasted, right? So what is it? I'm actually not going to go through the equations. This just actually describes how we teach our students, and in the end, it's actually conceptually very easy. I told you, you recycle the heat, and the plasma's sitting there, but that heat wants to leak out to the surrounding environment. So in the end, the balance is set by the amount of heating, which comes from the conditions of the plasma and the fuel itself, compared to this energy confinement time, which is basically just the time scale it takes to leak out of this. You solve this, and you solve it through understanding the rate at which the power is heating. And the key thing is that the amount of power you're making is directly linked to the amount of heating that it's making because it's fixed by the nuclear physics. So I'm just going to come to the high points of this. So the temperature is extremely high, but the density is very low. So this is why fusion is such an extraordinary, it's the second reason, but why it's so intrinsically safe, is that it has very low density. So the energy density of the fuel, which sounds like crazy, it's less than boiling water. There's no energy in the fuel. So when something goes wrong, it just stops. Because anything, literally a power plant that would run Saskatoon, if you went like that on it, it stops the whole thing. Because there's way more particles in your lungs than is in the fusion power plant. Actually, that turns out to be a problem engineering-wise. And then the fusion power is simply controlled by the plasma density. Like, how do you get this exotic fuel in there? It's literally a little gas line that comes, and there's a little stream of gas that comes into it. That's how you get the fuel into it. And the fusion reactions are sustained by heating, not a chain reaction, which I pointed out before. The last one is that why do we use deuterium-tritium fusion? And I thought there's logarithm plots. Well, it turns out what we need to do is push up vertically on that axis, and deuterium-tritium is by a factor of around 100, the easiest one to do. There's other fusion reactions, but they're much more difficult to obtain. So we'll get to the brass tacks. So in the end, we use DT fusion power, and in the end, all these factors are determined by three parameters: the density of the fuel, how long the energy is contained, and the temperature of this. So this sounds like, well, how far have you actually gotten in all this? Well, here's the key one. In fact, Dale, you asked about when are we going to get power out of this, right? So what's happened is we've actually made these conditions in the laboratory. Here's the plot. This is the same plot I showed before. Temperature is on the horizontal axis, and this confinement times density is on the vertical axis. These parameters uniquely determine the amount of fusion power amplification that you get. So you're going to get the fuel hot by heating power to the plasma. This is your loss of power. And then you get some back from the fusion that actually occurs. So obviously for a practical energy source, this has to be, in fact, well in excess of 1. For a practical energy source, it has to be in excess of 10, in fact. And then infinity is where a star occurs. So you go over to the plots, and you see that these blue dots on this are actual physical experiments we've done, including the ones at MIT. And this temperature right here, 10, is 100 million degrees Celsius. We've actually exceeded 100 million degrees Celsius in a laboratory that easily fits inside this room. But we didn't actually get to the point, the density and the confinement time were such that we were making net energy. We were right at, you can see the blue points are right up at the cusp of this, just about to get over into net energy gain. So that's the threshold we need to get over for this to be a practical energy source. So in the end, we'll summarize. Why do we pursue fusion energy? It's physics, right? As I said, the universe already voted. No polluting emissions. There's no carbon involved at all. The fuel is freely available and inexhaustible. It's hundreds of millions of years of fuel are available. You can generate it anywhere at any time. You can't have meltdowns. There's no long-lived nuclear waste in this fuel cycle. There's no proliferation around this. There's no fissile material. You basically supply energy for humanity forever with minimal environmental impact. So it's a unique tool. The physics of this says this, but it was too slow. That was its problem. So fusion had a conundrum, is that we understood a lot about this science, and we make this plot that, this actually came from our Sloan, our business colleagues. They say, this is way too complicated, Dennis. Put it on a plot. And the plot is up and down is up here. We have really high confidence in the science. And down there, it's like, no, like we didn't actually make this work very well. Like if you go back to here, there's this plot down here. Everything else, besides tokamaks, are like factors of hundreds of thousands away of actually attaining. People have tried like all kinds of magnetic confinement mousetraps, basically. Most of them don't work. It's like, but this one called the tokamak works spectacularly, but because of a limitation in technology, became enormous. And basically, they couldn't make a strong enough magnetic field, so to make up for the weaker containment, it got bigger and bigger, like going more towards like a star. So this is a project, which is a very interesting science project. You can't even see the person on there. They're less than the size of my finger. It's the biggest science experiment ever built by humanity, and it's taking 35 years. It's going to take 35 years. So, man, here's the other one, my friend John is economics. What's the other axis? Slow, big, expensive. For a practical. Science, okay. Economics, fast, small, and inexpensive. Well, good. People were trying these other mousetraps, but they were a factor of 1 million, hundreds of thousands away in science. So this is what you call leading the audience. Could there be something fast, small, and inexpensive and have high confidence in the science? Question mark. Excuse me for leading. So we looked at this, and it was, and I actually have to acknowledge that this came from a class that I taught primarily in engineering design. So my students, who were spectacular, I gave them, and I walked into the class in around 2015 and said, here's the new technology. I'll show you what it is. Basically laid it on the table and said, we're going to make fusion way faster and less expensive. So I'm going to challenge you to build how fast and how small can you actually make fusion work. And what was the technology? It was this. It was a breakthrough that actually didn't come from our lab. But in good engineering disciplines, like you recognize the advances somebody else's make and you put these things together. And it was a new form of superconductor. So why are these important? Because to make this electromagnet, you must use a superconductor, because otherwise the current that you're putting through the electromagnet becomes an enormous toaster oven, and you're losing so much power to that. It gets hot and you're consuming electricity. So copper, like the best conductor, is not even close to being able to make it. So you have to use a superconductor. Superconductors have no resistance, and so therefore when you make the magnet get going, it can run forever and not use any power. Most of us are familiar with this is an MRI machine. That great big hole that you go into, that's a superconducting magnet that makes magnets for fields for several years without any electrical consumption. And I'm going to skip a whole bunch because there's whole lectures just on the superconductivity. And what happened, like all this happens, is that it became commercial. This is a Nobel Prize in 1989, high temperature superconductors. And they were these small crystals, and somebody figured out how to put these onto tapes. Just like kind of like you put like films on solar panels and so forth. And these tapes exhibited this. And this is what you love when you're an engineer, is that what the superconducting state cares about is the temperature, usually it's near absolute zero, the magnetic field, and the current density. And the key thing was that most superconductors, if you elevated the magnetic field, it basically quantum physics turns off the superconducting state. And this material had the extraordinary property, it basically doesn't care about the magnetic field. You can just keep cranking up the magnetic field and it stays in the superconducting state. But people hadn't figured out how to make it a practical one yet. So we understand about why this is so important. Here's the physics of this. So remember I told you the magnetic field makes the fuel particles, spin around. The size of the particle orbit is set by only one thing, by the magnetic field. And the stronger the magnetic field gets, it shrinks the size of the orbit. So like that, and if you double the magnetic field, it shrinks to like this. Now, why is the size of this orbit important? Because that's the underlying concept of the confinement. So if you've got this, then you basically have to stick in around 500 of these to make sure that these particles, as they're spinning around, don't leak out too fast. So if it's that big, then you build it that big. Oh, but it's a three-dimensional object, so then everything gets bigger like that. So if you can double the magnetic field, that decreases by a factor of 2. With the same physics, basically every dimension shrinks by a factor of 2, and the volume shrinks by a factor of 8. And it's actually like a diffusive problem, so it actually's got a stronger power. Well, the one that's really even easier to understand is the magnet is actually exerting a pressure to hold this star in place, to kind of trick it. Again, and that force goes like the square of the magnetic field, but the fusion power per unit volume goes like the square of the plasma pressure. And the key metric here is the plasma pressure, which wants to escape, to the stabilizing magnetic field. So it's sort of like this cartoon. It's like bursting a balloon, right? And so if you can increase the magnetic field by a factor of 2, the magnetic field pressure goes up by a factor of 4, and the fusion power density goes up a factor of 16. So this is the key economic driver, of course, then, because if you can make that much power in a smaller object, this means it's a sort of a 20 to 40-fold improvement in the cost per watt in one fell swoop. And that was what happened. We realized with my students, who are now running one of the most successful companies, energy companies on the planet, we realized this changed everything if we could just double the magnetic field. It wasn't actually just the final power plant, which we designed. It was the way that you got there. It short-circuited decades, basically, of research to be able to get there. And here's the visceral one to do. I'm not going to explain all the reasons, because just trust us, we did the math right. And in the end, this was the ITER device. You can see the person standing beside it. It's being built in the south of France right now. It's 15 years into construction. It's going to take another 15 years to complete. And we figured out that this object, all to scale, actually achieves exactly the same physics and energy mission as that size over there. Wow. If you could double the magnetic field. But something else happened. It wasn't just an innovation in science. It was an innovation in how you get there. Because if we could get there that much faster, and the world really needs fusion energy, why don't we actually also remake the model about how we get there? So we did a major organizational innovation. And people spin out companies all the time. That's what we realized. The commercial aspects of this were much closer than people had imagined before. But we had, sort of order of $1 billion of federal investment, government investment in our laboratory at MIT. Why turn off all of that talent and infrastructure and just launch? Because we knew we needed a company, because if you're going to make a commercial product, you need a company. So we launched a company called Commonwealth Fusion Systems that had this very targeted plan: build the magnet, show net energy works, commercialize. But we went to these people, some of the world's largest energy companies. People always ask, what do the oil companies think of this? They're one of the major investors in what we're doing. These people that you see on the bottom, a few of the faces you might recognize. And we said, we're going to do this differently. We're not only just going to launch this out. We're actually going to launch the whole effort in parallel. So it's the idea of which so I don't have a role in the company. The idea is I'm running on the university side the things that are needed in a mature energy industry, but thinking about that energy industry before it's actually made. And whoop, up together, the business and what I call the ecosystem, all pulling up together, all at the same time, and particularly early on, making sure that we can do this magnet development as fast as possible. This is a whole new model. We basically leverage this $1 billion. We have over 300 people working on this project now at MIT, and the idea was we actually coupled early on the company and our lab at MIT, much closer than it was what is usually considered around this, because day one, there were 50 people from MIT working on this, and we had the infrastructure to be able to do it. The teams worked side by side, and we actually worked out an intellectual property arrangement so that we could co-invent the technology, and the people at the university, at the company, could work with the people at the university, and once it became commercial, and literally it's happening like as we speak right now, they're building the identical things out in the commercial sector, which we can't do as a university. So tech transfer was a month, not years. Because speed was the key aspect to this. So what did we do? So here's some fun pictures. So I took the largest experimental hall at MIT and just converted it into this mission because it was so important. So we got rid of a whole bunch of power supplies. It's hard to see. You can see the people crawling around in this. So this was 3 guys in a garage are not going to solve fusion. It's big things, right? And we're making it small already. And basically we built this thing that was allowed us to do all the things that you need to do to be able to test superconducting magnets. 40,000 amps of current through this. Be able to cool things to 20 degrees above absolute zero and so forth. I won't go through all those. And we built it. It was interesting. I mean, I sit on many National Academies panels as well too. It's interesting. And the experts all said this will take at least a decade. And we did it in 2.5 years. And that's actually the difference also about bringing in a company at the early stages. So it was interesting. We also made it existential to both organizations. Sam can tell you I didn't see much of them. Last summer on that one, it was day and night, 24/7. And we did it. Here's the magnet right here. And the short story is that we basically doubled the magnetic field compared to any superconducting magnet of this scale that had ever been built before. So this is not a factor of 2 win. It was a factor of 40 win in fusion economics from one day to the next. So the fusion world changed overnight because of this. And it was fun building this thing. It's about 10 tons. There's about 300 kilometers of this HTS ribbon inside of it, about 2 meters tall. And it had a special design, which I'm also the most, not just the fact that it reached 20 Tesla, that when we coupled the energy, the university lab and the company, we thought it was very hard tech. We actually reinvented superconducting magnets. There's something like 30 patents involved in this now. Because and very much in engineering design class, like we just threw out the book. Like we went and talked to the superconducting experts and we just threw them out of the room. They said, let's get down to physics, because this is actually physics at its heart, and this is a totally different superconductor. So we just threw the book out, built it, and for example, it's completely modular. It's actually made of 16 subcomponents that are then put together afterwards. And anybody who's built real things realizes building things modular is like, you have to do it this way. You can't build enormous monolithic things for a whole bunch of reasons as well. So September 5th, Labor Day weekend, 6 a.m., past 20 Tesla. What happened? Well, it wasn't just that we did that. It was also, at the same time, we coupled like the university expertise in like modeling. So we built the world's most sophisticated supercomputing model for a magnet. And it's actually more complicated than the fusion plasma ones. In fact, I was just talking with John. Remember the computer lab up here? This thing was cranking on supercomputers. In fact, it was faster to run the experiment than to get the supercomputer model to converge. But we ran them in parallel, and it actually basically confirmed all this. And in the end, what we used was if anybody knows about magnets, like if you take a magnet like in your car, you'll see it. It's a coil. And basically, it has a wire that runs around. There's always like a sleeve around that wire, because what you're doing is you're forcing the current to go around and around and around like this. We got rid of the sleeve. There's no insulator inside of the magnet. So well, how is it a magnet? It's because we trick it. Because we trick it by the fact that the steel is actually an insulator, because the superconductor has zero resistance. So all the current is forced actually to go in a loop, even though there's no insulator inside of it. So this eliminated all high voltages in the system. And in fact, it never went above a tenth of a volt. So we're actually revealing, you're one of the first audiences actually to see this stuff, because now we're getting out into the world and telling people about it. It was a little weird actually being a little secretive about this, but we're out telling people now. So what did this mean? So what did this all mean? Well, we knew about this aspect of the high field was going to work, but we didn't have a way to get there. In fact, we had done these experiments on our experiment at MIT, which had used copper. But when we ran this experiment, as I said, it almost fits like on this stage. Over 100 million degrees, 300 trillion fusion reactions per second. Like fusion is real. That was on a university lab, but it consumed 250 million watts of electricity to make the magnetic field. And when we turn this on, which is actually about the same size as that magnet, it consumed 25 watts. And there's the answer. So it's the same physics, now ready to get going. So people got pretty excited about this story, and then the company that we had spun out went out and raised $1.8 billion from the private market. So all of this is funded all solely through the private sector. And now we are busy building this, which is called Spark, which basically takes this magnet and that physics, puts them together in a device that size, and it will make about 100 million watts of fusion power and achieve, to your question, it will achieve net energy for the first time. We've actually never seen that. And why are we doing this together with the university? Because we've literally never seen that phase of matter ever on Earth. That when it's a star on Earth. So when it becomes self-regulated, it actually has different kinds of science that are with it as well too. Oh, but very, very important, because in this all along was not that magnet, and neither is it spark. It's commercial fusion on the grid. And so this is what we designed in my class, which is called ARC. It's not named after Iron Man. I just have to say that every time so the copyright lawyers don't get us. And you can see the person beside it right here. It takes this magnet and it adds the extra bits which are actually required to make a practical energy system. That will produce around 500 million watts of fusion power. And that would easily power all the energy supply requirements of Saskatoon. Oh, and by the way, and the cost of fuel per year would be about 10 cents. So why is this exciting? So what is Spark? So Spark, again, we call this the Kitty Hawk moment of fusion. It's 100 million watts. Energy gain is about 10. And the reason we can do it is because of this new magnetic field. But it's also, it itself is not isolated. It's actually because it's being done by a commercial sector. Everything that is around Spark isn't, we're going to do some cool science, but it's really to provide the economic basis for going towards commercialization. Actually, I'm going to skip that. Oh, well, this is for a more plasma physics. Basically, in the end, you can think of it's kind of like a wind tunnel experiment in all these. It turns out that we've actually done the science, essentially, of Spark already in existing tokamaks. But we didn't have a pathway to actually get there. We're quite confident that the science will work. We just got to build it, actually, in time. So what's happening? Well, we're concentrating on building it. So it's happening. It's in a commercial site around 45 minutes northwest of Boston. It was too big to put in Cambridge. And I'm very proud of this, is that, the first thing that you think of is building this exotic magnet and tokamak. That's it over there. It's actually one of the last things being built, because the first thing being built, that building there, is the magnet manufacturing capability. And I told you about tech transfer. Like that magnet that we just showed work, like last year, is going to be filled and be able to make hundreds of those a year in that facility. That's going to be how we're going to have impact on this. Then finally, I want to talk about ARC, because, boy, Dennis, this is so exciting. Like, we're just all ready to go, right? No, well, not quite. Because what this is going to give us is, I say, the Kitty Hawk moment for fusion. You can fly. But there wasn't like a reclining seat and a video screen on the Wright Flyer, right? It's not a commercial product. So we have to get to the point, and what do we need to do? Well, ARC is and that's our commercial idea. So it's basically it's the size of tokamaks we've built already, in fact, around the world. But we have to start adding in some extra things, which really means about capturing the fusion energy and putting it on the grid. And most of this is around, remember Mr. Neutron flying out with 80% of the energy? Well, there's another innovation that we did with my students, is that we realized that's really, really bad for materials, because when the neutron comes out and is bouncing around in the materials, it'll damage them, it disorders them. Oh, why don't we pick something that actually doesn't care if it's disordered? Oh, we know what that is. It's called a liquid, because it's already disordered. So we basically stop the energy in this liquid blanket and convert it into power. But everything in this is set by market economics, dollars per watt. And in the end, we actually need, and this is probably going to be the hardest part of this, is that now with this magnet in place, to get as fast as possible, any new energy system always has hiccups. These are complex integrated engineering systems. How do you get from this to high reliability? And we already know some of the challenges of this. We've increased the power density by a factor of 16 in theory. How do you actually get heat transfer to work at 16 times higher content? Because if you don't do that, you're leaving economics on the table. How do you get availability of the materials? That's a very hard part, because it's a very harsh environment. As I said, it's kind of like putting things on the surface of the sun. So how would it all work? So basically, as I said already, you make this high field electromagnets, which is the things around. The plasma creates fusion at around 500 million watts. Neutrons heat the molten salt, which is surrounding the plasma, and then you extract the heat like a normal thermal power plant. So this is the third part about fusion. It does not take a reinvention of anything of our present energy systems. You can literally replace coal-fired power plants with this, because it makes heat in the end. And that's actually what most of our energy system is there for, is to take heat and use it for something interesting. It's just that now the engineering topics, which I'm starting to work on, because we kind of did these magnets and so forth, is actually now this whole new area. In fact, I gave this talk at an engineering college in Penn State, because I'm saying this is a big ship for everyone to get on. I know it all sounds exotic and plasmas and suns and all that. Now it's actually, really, really important things. There's a much larger expertise out in the world. Materials, heat transfer, corrosion, molten salts, chemistry, chemical engineering. It's actually pretty much every engineering discipline that I can think of is involved in this. And that's actually what it's going to take to actually not only make this work, but make it work as fast as possible to get to the economic targets to make it reliable. Actually, I'm going to, just for time, I'm going to skip this one. But basically, we've started, this is so exciting, we started to work on this already. I was pretty sure we were going to make this work. So I started gathering more young teams, more students. And so now I'm bringing in people. We have 40 graduate students coming to the Plasma Science and Fusion Center in the fall. Oh, yeah. And what we're going to work on, a whole bunch of them are not going to work on any of the quote-unquote exotic stuff. They want to come work on the practical engineering aspects and science aspects of this. And this is including, for example, being able to capture the fusion energy and make that fuel. We've actually never demonstrated it in the lab at any kind of scale, because everyone knew fusion was 30 years away. Now it's 5 years away. Let's get going. I'm going to skip this. If you're interested in these, we got some really cool ideas of what this is going to do. And I want to end with this one, which is, I think, the biggest one, actually, and where if there's some clever mechanical engineers, material scientists, it's heat transfer. This is our biggest limitation right now. As I said, fantastic. Physics allows me to increase power per unit area by a factor of 10 to 16. I have no bloody clue what to do with this power. It's like 2 million watts per square meter when I do a great job of distributing it. Sometimes the local heat gets to around like a half of what it is, like at the surface of the sun. All right. What are we going to do? Well, standard materials and like, here's what I say. Taking a block of, the engineers will appreciate it, taking a block like this and putting a round hole in it and pouring water through it is the dumbest thing you could imagine for getting effective heat transfer, but that's what everybody's building. It's like, no. We need to come up with like total innovations of like the things like heat pipes, for example, that achieve much higher heat transfer. And this is one of the kind of crazy ideas I had, woke up at 3 a.m. in the morning with this one, is it basically got rid of most of the solid materials and tried to start using convective heat flow. It's almost like a mixture between an MHD pump and a heat pipe. So there's some ideas of liquids. I'm not going to go through it. Anyway, we have this enormous number of innovations which are coming. And by the way, a whole bunch more companies and expertise, because this is literally a new energy industry when we make this work. So all the things that are going to be associated with fuels, materials, supplies are going to be needed to actually lift this up, because what we're again racing against is time. So I'll end here just to see is that this is why there's so much excitement about fusion right now. And we're right here, and our idea is to have this on the grid in the early 2030s. But to get this to be a meaningful in climate change and to people's lives, we need a big, big effort about going. And I'm just thrilled that you were here to hear about this. So thank you very much.
Okay, we have time for questions. So I'm delighted to open the floor because this was just fabulous. Mike.
You thought, well, okay, Carl Sagan says we're all made of star stuff.
Yes.
So you're spitting out helium. Is there a potential to take that helium as an input to another reactor, which will spit out X lithium or whatever, and continue around? So can you have a tokamak shaped like a intestine and poop out helium, whatever,
Yeah.
the next one?
Yeah.
Okay, so I'm going to repeat parts of Mike's question, and I'm going to ask people to go to the microphone for subsequent questions so the people that are logged in can hear the questions afterwards. But the idea, if I understood correctly, is can we take the helium and pass it forward to another reaction so we have an easier time capturing the energy? And I'll let Dennis address the intestinal questions.
Yeah, that's quite the analogy. Yeah, so this is actually, so most people are not aware of this. Yes, we are, the interesting elements in our body were made in the interiors of stars. It's nucleosynthesis. So it's how all the heavy, because the universe started as hydrogen, effectively. So how does this work? Is that the short answer to your question is no, because that requires effectively supernova. Because those are the principal means by which those, because you need a major energy excess to actually make the helium go further up the chain to make those. So those are beyond we can do those in the laboratory with an accelerator, but they're not part of the energy bounds. So we're just very happy in the end, like a normal star, like our own sun, doesn't really make those heavier elements in any abundance. So we're just happy to make helium. That's in the end, yeah.
That'd be great. Thanks.
Dennis, this always amazes me. And as you speak, it seems like this has been a gilded path from Cheriton, Saskatchewan. Has it always been this easy?
No. Actually, I almost quit 10 years ago. It was because, why? Because while I liked the science, I couldn't see any way this to go forward practically. Like I was stuck in this horrible place. None of my students, I was interesting when I was hired at MIT to, as it happens in universities. Why do we have universities? Strange mixes of interesting events that happen. I was hired at MIT as a professor to be the liaison to ITER for MIT, because everyone knew that was going to be the sole fusion experiment in the world pretty soon. And MIT is a leading institution, wanted a role in the leading fusion institute. And after around 2 or 3 years, I realized I was probably going to die before that actually came to fruition. But it was even more than that, is that there's this enormous need and potential for fusion, and it wasn't being realized. Because we were stuck in this place where, although it's not a hit against ITER, it's just the fact of what it was. The idea that it was going to be another 30 years. So I didn't have a single student interested, actually, in working on this project. And I looked around and said, I should do something that's practical and impactful. And I can't see which way it is. And then I was walking along the hallways at the university. It was a colleague who I don't really work with that closely. And what was he carrying in his hand? I said, what is that in your hand? He goes, that's high-temperature superconducting tape. It's like, which I'd never heard of. And I looked at this, and I started to look up the properties. And then around 2 weeks later, I walked into the class, I threw it on the table and said, we're going to change fusion with this. And that's what started. So, yeah. And that's why you have universities, by the way, right? It's an interesting question. We were talking about this on this weekend. You have universities for these totally unexpected, unpredictable combinations of ideas that come from people working in vastly different, like why do we have, a chemical engineering one beside a physics department, beside a geology department? Because these things happen through these intersections that are almost impossible to happen at a place that's not a university.
100%. Go ahead.
So I find your story fascinating, and I want to know more about it. So you talked about patents, you're talking to us today. So how much of this is now sort of publicly published and available for us to
Yep.
go and dig deeper into what you're talking about?
Yeah, so the patents are almost all completed, so you can look those up, yeah. Around the so-called Rebco superconductors, yeah. And they're filed by MIT and the company that we have. So you can go look at some of those details. And it's fascinating, by the way, because it was a very difficult integrated engineering task. So for example, one of the greatest challenges, remember I said that the magnetic field exerts a pressure on the plasma to kind of contain it, but it actually exerts that pressure on itself. So when you double the magnetic field, the forces on the materials go up by a factor of 4. So you have to be very, very clever about how you deal with those. And how large are those forces? Well, that magnet that I showed, this magnet here, right about at this location over here, had 900 megapascal of local stresses. So for those familiar, 900 megapascals is 9,000 atmospheres of local pressure. It's like, this is close to the ultimate yield strength of most steels. But we came up with clever ways and cryogenic material properties and so on and so forth, and we figured that out, so yeah. You can't just solve one problem at a time. That was what was difficult about this, on this.
30 patents.
Yeah, because it was a reinvention. It was actually a totally new, it wasn't just like a particular detail, it was actually in a total new philosophy about how you design the magnets. And most of it was around how, we're pretty sure we can build one of these and show that it works. How do you build 10,000 of them? And part of that was around the modularity of the design. And it's actually, in our own team, it was fascinating. Like the first sub-component that we built took us like 6 months. And by the end of it, we were doing those in 1 week. Yeah.
Hi, actually, I have a question about scalability, and I think you start answering it. I guess vision past 2030, let's say if everything goes really well and we have 500 megawatts on the grid, is the idea to increase the output of each individual unit, or to actually make unit modular and very affordable that we can spread those around the grids?
The latter, yeah, the latter. So the idea is, this is one of the other innovations that we came up with. Everyone knew that fusion would be multiple gigawatt plants. And I said, well, why is that? Well, in some sense, the science of fusion gets much easier when you increase the power output. Because it relies on its own heating. This is actually why there's a minimum size for stars, actually. Because at some point, it just doesn't heat itself enough, and basically you get a dud star, right? But that does not work in the actually in the economic way. So right now, the electrical sector wants 200 megawatt electric power plants, and in the end, also economics requires modularity of these units. So that's the idea for electricity generation, is that you basically build around 5,000 of these, and you can do that if you get going fast enough, right? And that's actually why our target is the early 2030s, because if you take the so-called S-curve, which shows you about how technology ramps up, and you get a scaling rate that goes with this, by 2050 you can have like many thousands of these, and then that's making, that's hard to do, and it's very hard to do, but it's within reason that we might be able to do that, and then that means it would have an impact on climate change, for example. But now you asked about that's for electricity. So one of the other, and in fact, my next design class is coming up this fall, and I've got a whole bunch of ideas about what the next one is going to be. And some of them are around not making electricity with this. Remember, I told you it's a heat source. Yeah. So what's one of the biggest, and by the way, we are still delusional as a society about how hard decarbonization is going to be. Mm-hmm. It's the hardest engineering science thing we've ever tried by a lot. It's so hard. Why is this? Because 85 to 90% of our energy use is fossil fuels. This is not electricity. People think replace electricity with renewables. That's 20% of the problem. How do you decarbonize air travel? So one of the ideas is let's take this technology and actually go to Europe, scale it up a little bit. And so like Logan Airport, which is the Boston airport, consumes around 4 gigawatts, 4 billion watts of fuel energy per day. This can actually produce that. So, but you would turn it around, and instead of putting it onto the grid, that's too big for the grid, you start making carbon-free fuel, and it's hosted out on the corner of like the tarmac, and it's basically you supply the fuel to the jet airplanes. I have no idea if it's economical, but I'm sure we'll find some fun things to do about that.
Mike, go ahead.
Who is your $1.8 billion sugar daddy? Where do I invest my
Where do you invest?
retirement plan?
So, man, it's like right to the bone. That's good. That's what I like. Good. Yeah. So it's interesting. So I really have to give props to our first major investor. The first company thing to believe in us and actually put money in was the Italian national oil company, Eni. And their CEO and their leadership had the vision to say, we have no idea how we're going to decarbonize. We're going to take a bet on you. So they were one of the first investors. Then it became leading venture capital people. It was a mixture of this. Now at the 1.8 billion, there is no sugar daddy. In fact, when we set this up, we were insistent that this was not going to be sitting in the hands of any one single entity because it's too important. But when we did it, so by the way that we did it, and it said, somebody asked about the patents, I can also tell you, just go online, Journal of Plasma Physics, Spark Plasma Physics Design. We paid this for be completely open access. The science of this is 100% accessible to the public. That we're not hiding things in this, right? This is about, you still have to run a business, but you can still do it in the right way. So by the way that we did this and the coupling to MIT and the strength of the science and engineering in this, what happened was it was sort of a fundraising round that people, I'm not in this world of fundraising, but people had never seen. It was the combinations of the world's biggest energy companies, the world's richest individuals, but also venture capital firms, but also sovereign wealth funds, which came in this. So there's something like 50 different investors in this. And the capitalization is such that they can see this through. Not just building Spark, but to actually deploying thousands of these power plants around the world. It's a good question, and it's private right now, so there's no you can't actually. Holy cow! How you doing, Glenn?
Good. How are you doing, Dennis?
I haven't seen him in a while.
Yeah, it's been a while. So.
Remember Professor Schott's class on fusion, or Professor Skarsgård's class on
Yes,
fusion? Yeah.
of course.
Yeah.
Of course. Very, very interesting talk. I think all the plasma physicists left, and as a space physicist who sat on plasma physics defenses and whatnot, I might have a couple questions for you. So I guess, as I've always said, I'm not a plasma physics fusion guy, but yes, you're making the sun, trying to put the sun in this room, for example. So,
Yep.
I guess one of the thing is quenching of plasmas is always a big problem and whatnot. So, I mean, I guess obviously getting a lot higher electric or magnetic field allows you to confine the plasma and whatnot. But I mean, keeping that heat in there. I mean, obviously you want to keep it in there, but then you got to get the heat out to make to run your steam engines or your turbines or whatever. But so I guess again, and this will be my bias as a space plasma physicist who just looks at instabilities. Is that that must be a big concern for you? Yeah,
it's a great question. So it gets more technical. In fact, it was in that scatter plots I didn't have time to really discuss. So in the end, this magnetic field that we're supplying, there's many different magnetic fields which are in the plasma, and there's this whole zoo of instabilities and so forth. But we've studied these, for 30 years in this particular configuration of the tokamak, and we know where they are. You can't arbitrarily just increase the pressure or increase the density or the temperature. These instabilities will appear, and we know these in great detail. But in the end, This magnetic field that we're supplying with these coils right here are the stabilizing magnetic field. They're actually not the containing magnetic field. It's a little counterintuitive, I can explain it. But and what that does is that when you increase the magnetic field, you move the plasma, even though the temperature and the density go up, you actually move the plasma further away from those stability limits. So we ran in this experiment right here. We actually ran those. So we achieved like the highest pressure, for example, in a thermonuclear plasma. It was 6 atmospheres of pressure, but at 100 million degrees in the center of that. But it was being done at high magnetic field, and there were 0 instabilities in the plasma. So that's the science part. It's a good question, right? That's the science part of it. This is also why the practicality of fusion when you've got higher magnetic. So there are other approaches which sit right at the very hairy edge of the stability margin. Ours we're factors of at least 2 away from all the stability limits. But then your other question is the right one. It's like the problem then is once it's stable and cranking out all this power, how do you get the power out? And there's a really simple, it's a very simple challenge actually, is that because the primary requirement is you make containment, the physical shape of the device is such that you minimize the surface to volume ratio. Because the plasma is a volume process and the losses come out through the surface. So what's the best thing that you can build? Well, a sphere, right? Or in our case, it has to be in the shape of a toroid. So you build like kind of like a big fat tire, donut like that. Great. But where does the heat come out? The surface. So the things that are on the surface get concentrated power because it's impossible to put physical objects inside the fusion device to actually take it out. So this is why I said like heat transfer problems is now, in my opinion, the largest impediment to actually practical power sources. Yeah. So it's right on. Yeah.
Okay, no, that's really interesting. And so there's the stabilities. That's interesting that they're solved. Then are there any other like the dirty plasmas, like the particles going to the walls and creating ash and whatnot from that? I assume
Yes.
is that still an issue? I think it is a big issue with ITER, isn't it? Or?
Yes, it is an issue. So in the end, and this is something we have so this is what, before I became the director and went down this, that was my area of expertise, plasma material interactions, where I worked a lot in this area. So in the end, this is it's almost like a corrosive environment for the interior materials, and it's basically going to rearrange them at some place. So we don't know, we've got some ideas about how to control that, but it's very difficult to predict it because we've never actually built it. So one of the things that is in this device here called ARC is the ability to actually rapidly change the wearable materials inside of it. Because when I looked at this, I said, I had the same skepticism. It's like, there's no way we're going to design this out of unobtainium and that this is going to last for years and years. So if you build a car, you asked a good question, John, like it's like, if you have like a car, I think one of our friends had a car dad or something like that. Remember, he's like, what kind of design is this? Like that they had to lift like the motor out of it or something like to change the spark plugs. That's a stupid engineering design because you're going to have to change the spark plugs. Our spark plugs are the interior surfaces. So what we sat down is we worked out a whole set of technologies that said, those are going to fail. They're probably going to fail quickly, but there's a pathway forward to actually making them more reliable. But the pathway can't be that it takes like an ITER, it takes you 3 years to change those components. In our device, it takes a month. That was another innovation about this. And again, it came from the engineering design class because I kept insisting this has to be modularized, and you can't. So anyway, that was a short way to saying that there's a whole bunch of innovations around things like that about making practical energy systems, which require these kinds of overall design philosophies of making practical pieces of equipment.
Thanks a lot.
Okay,
I'm going to
thank you
give the
very much.
last question to Terry Fonstad.
Thanks, Dennis. That got me all pumped up and excited. The one thing I'm still out there is you talk about putting this on the corner of a airport.
Yeah.
So what are the safety issues around this? Because this seems like it might be a little disruptive to the small modular reactor industry.
Yep.
And in a few days or months or weeks, it's going to cause a bit of a tizzy in the investment community if this is coming along in 2030 instead of 2050. And so the only thing, I'm an environmental engineer, so I think about impact assessment and where can I put these things and what's the public going to say. And I'm kind of excited all of a sudden today. So
Yeah. Well, it's a very important part. It's actually, so, thanks for the question. So I'll go up. So it's another part of my, I think I'm going to be giving a lot of these talks. So it's part of my role is to get out and explain. It sounds so mysterious and like obscure. Like, no, you can understand the basics. I'm not going to get into the details of it. Like, what in the end does this look like? In the end, we convert hydrogen into helium, right? But the practicalities of it are such that there are other situations involved. So, for example, the tritium, the reason it's not on Earth is because it actually decays after 12 years into helium-3. And helium-3 is stable, it's fine. But this means that it's a radioisotope, right? So if you release this into the environment, you can have environmental health concerns and people health concerns. So that's probably the biggest one that comes into this. So what we're looking at is, so to make, in parallel with making it economical and practical, we also have to make it acceptable to people. And part of this is, in the end, you can, how do I say, fission is difficult because the things which make fission difficult from the safety point of view and for the public's acceptance point of view, you cannot get rid of because it's physics. It relies on a chain reaction, which means there's always some possibility of it running away. And the fission process must make these radioactive isotopes that have tens of thousands of years of requirement for storage. It's in the physics. So fusion doesn't have that. Fusion fuses these together and makes helium. The things about what happens about its practicality with respect to the environmental movement and for it to come into a community and use this is in our hands as engineers. And namely, is that if we're really clever, we can keep making the environmental footprint smaller and smaller for this. Again, it went way too quickly. The idea, for example, is the amount of tritium fuel at a particular power plant. With clever technological choices, we can actually drive the inventory down and down and down. And why is this? Because the physics tells you that the total amount of fuel that's actually being burned at one time in the core of this is 0.2 grams. 0.2 grams. That's smaller than a chickpea. And that can power Saskatoon. It's like, so the stuff that's on the outside, let's get clever in engineering about it. So what we can do is have this acceptable to the public. Because if we don't do that, then all this work is wasted, actually, as well, too, right? So then that takes a larger conversation with everybody in the community of realizing, it's not a panacea, it's still a technology, but it's got this physics that allows us to just play this completely unique role in tackling climate change. Like, how can we leave this on the table as a society? Like, we have to try this.
I've got all sorts of people want to talk, and we're going to run out of time. Desperate for one question. Go ahead.
Easy, short one.
Yeah, for sure.
Dennis, at this point, with what you've talked to us today, and maybe the grid by 2030, at this point, would you put any money into SMRs?
Yes.
Oh yeah.
Yeah, absolutely. Because we need carbon-free energy like now, right? In fact, it's one of the things that just keeps me up like at night is that we're not going fast enough still. And we're going to hit some bumps in the road. Like, this is our aspiration. This is hard, right? It's actually one of the things that right now I'm doing at MIT is the realization that we have totally the wrong workforce and expertise in fusion. So a huge challenge in this, and it's actually why I'm going to be going on and talking to lots of engineering schools, I'm already doing it, is this takes a much deeper bench than what we have right now. That's actually what's going to stop it. And it's interesting, many of these areas overlap with our colleagues in fission because there's similarities in the disciplines of which they do. So SMRs are an interesting pathway. I think their biggest challenges are twofold. One of them is economics. Actually, even though fission is much more mature than fusion, its economics are still not that great. And then one that comes to the question that's just before. Will we get to the point where, as a society, we're feeling comfortable actually about using fission because it just has to have greater safeguards involved from the physics that's involved. But it's in the end, again, I'll come back to physics. My training in physics in the end. It's like, it's really easy. These are the two only energy sources where you get 20 million times more energy out per unit mass than fossil fuels. It's the only ones, fission and fusion. Like, how can we leave these on the table, right? That's what I would say.
Well, A big thank you, Dennis. That was just fabulous. I want to highlight a couple of things for the people in the room. You get to hear a talk like this maybe once every 10 years, so it's a real privilege to be here today. And I've heard lots of talks in my career as an academic, so thank you for that. One of the trademarks of an exceptional speaker is that they're speaking to everybody in the room, from the rhetoric teacher to the AVP research. So I think everybody was following along, super excited, learning at different levels. Couple of the things that I want to throw out as a challenge to the academics. There were 3 points that were made that were outside the physics. One, we started to co-create with business because we had to move faster. So we fundamentally changed the structure of how we think about IP and partnerships. 2, we threw out the textbook because we realized we were going into a really important new area. And 3, without public policy and public engagement, we're not going anywhere. So I throw out to the instructors in the room, we've baked these ideas into the first year program. I challenge all of you to take them forward, implement them in your classes, continue to have this kind of vision for the future, because we are in for a bit of a wild ride, folks. We really are. So thank you again. I have an award, a little, there we go. On behalf of the Cheriton family, something you can take home and put in the lab.
Oh, thank you very much, yeah.
And I did have the privilege of meeting Ross Cheriton before he passed, and I know he'd be thrilled by this. One of his kids went off to Stanford and helped start Google, so they're an exceptionally intellectual family too.